In the previous video, I introduced you to the idea of the amplitude of an oscillation. Here's the idea. Let's say we have a mass which is attached to a spring. The mass moves back and forth along the x-axis. The spring is in its resting position when the mass is located at x equals 0. So what we're going to do is we're going to grab the mass and pull the mass out to a position x equals a, and then release the mass. When we release the mass is going to oscillate back and forth between x equals plus a, x equals minus a, x equals plus a, x equals minus a, and so forth. This quantity a is what's known as the amplitude of the motion. Generally speaking, the amplitude of an oscillation is the maximum displacement of the oscillating object from the resting position. So in this example, the resting position is x equals 0, and then the mass is oscillating back and forth between x equals plus a and x equals minus a. Notice that in this situation, the mass takes on its maximum speed as it passes through the resting position. As the mass goes through the resting position moving leftward, it takes on that maximum speed moving to the left. As the mass passes through the resting position moving rightward, it takes on its maximum speed moving to the right. We would like to figure out what is that maximum speed. We're going to do this using conservation of mechanical energy. So here's what we do. Let's just say that this top picture here represents the initial position. And let's say that this middle position here represents the final position. As usual, we start our mechanical energy calculation by writing out expressions for the relevant energies in the initial situation and in the final situation. So here, the relevant contributions to mechanical energy are the kinetic energy of the mass and the spring potential energy. So in the initial situation, we need expressions for kinetic energy and spring potential energy. In the final situation, we need expressions for final kinetic energy and final spring potential energy. So why don't you pause the video and see if you can fill these out and then rejoin the video. Okay, in the initial situation, the kinetic energy is 0 because we release the mass from rest. However, in the initial situation, the spring is extended, so the potential energy stored in the extension of the spring would be 1/2 the spring constant. Then we multiply by the extension of the spring squared. Well, here the extension of the spring is given by the amplitude a, so I'm going to put in a squared. Now let's look at the final situation here. What is the kinetic energy of the mass right now? That would be 1/2 the mass times the square of that maximum speed. And also in the final situation, the spring potential energy is 0 because the spring right now is at its resting length. So I will put in 0 for the final spring potential energy. Now to wrap this up, let's apply conservation of mechanical energy. So we have change in kinetic energy plus change in spring potential energy is equal to 0. Change in kinetic energy would be final minus initial, which is then 1/2 the mass times the maximum speed squared. Change in spring potential energy would be final minus initial, so minus 1/2 Ka squared. That's equal to 0. First, we can multiply through by 2 to cancel out those 1/2s. Then in the next step, I'm going to move that Ka squared to the right. Now to wrap up, I'm just going to divide by m and then take the square root of both sides. And when I do that, I get Vmax is equal to the square root of Ka squared over m. And typically what we do here is just pull that a squared out of the square root where it just becomes a. So that gives us that the maximum speed is equal to the square root of spring constant over mass, and then multiplied by the amplitude of the motion. You may be wondering why I bothered to do this, but in the next video, you're going to see that this equation becomes crucial in developing a fuller conceptual and mathematical understanding of the motion of the mass on the spring.